Okay, 1.2 characteristics of polynomial functions. So in general, polynomial function graphs consist of a smooth line with a series of hills and valleys. The hills and valleys are called turning points. Each turning point corresponds to a local maximum or local minimum point. So we're going to experience local minimums. They occur when the graph changes directions. The turning point, it goes down and then comes up. Okay. Local maximum is when it changes direction by going up and then going down. And then we look at absolute minimums, the lowest y value on the graph, and it can occur when the graph changes direction, or it could be at an endpoint. And the same thing for an absolute maximum. It's the highest y value on the graph, which could occur at a local min or local max at a turning point, or it could occur at endpoints. So just to visually show you what I mean, so you can have a graph defined with specific endpoints in mind. So it cuts off here, and you would say, okay, that's an absolute maximum, because I can see that is above every other point. Absolute minimum down here could be represented by one of the turning points, because there is no other y value below this y value. Okay, and then you have your other turning points, local minimums, because it's locally, that is a minimum point, locally maximum point, locally maximum, local minimum. Let's assume this stays here and ends here as well. Okay, otherwise this wouldn't be an absolute maximum. All right, let's look at zeros as well. So a number of zeros. A polynomial function of degree n may have up to n distinct zeros. So if it's fifth degree, it can have 5 zeros. A quadratic is degree 2, it has up to 2 zeros. It can have 0, 1, or 2. A polynomial function of odd degree must have at least 1 0. Okay, and a polynomial function of even degree may not have any zeros. All right, so why is that? An odd degree function is always going to pass through the x-axis, right? It has to cross. So you're going to have to encounter at least 1 0. And a polynomial function of even degree may not have any zeros because the turning point could be above or below the x-axis, and it may never ever cross. Okay, the maximum number of zeros of any polynomial is the same as its degree. Okay. Shape depends on the degree and turning point. So a polynomial function of degree n has at most n minus 1 turning points, and I sort of alluded to that in the last lesson. So if it was a third degree function, it could have at most 2 turning points. It doesn't have to exactly have 2 turning points, but at most it could have. The shape of other graphs depend on the degree of the function. 5 typical shapes are shown for various degrees, where n represents the highest degree of the function. So linear function, n equals 1. For degree 2, quadratic. Degree 3, you can have a cubic. For 4th degree is a quartic, and for 5th degree, a quintic. Okay. Now, I'm going to show you a little trick to use that you could use to find the leading coefficient, and not just the sign of the leading coefficient, but the actual value of the leading coefficient. And to do that, I need to introduce to you factorials. And if you took data management this year, you may encounter this this operation as well. So n with an exclamation mark is called n factorial. And what that means is that you're going to multiply a series of descending natural numbers. And remember, what natural numbers are just whole numbers, but you're not including 0. Okay, it's from 1, 2, 3, 4, 5, etc. And no negatives either. So for example, 5 factorial will be 5 times 4 times 3 times 2 times 1. And you multiply that. So it's consecutively decreasing natural numbers until you reach 1. And when you multiply those out, you get 120. 4 factorial, 4 times 3 times 2 times 1, 24. And in the case of 0, we have to kind of arbitrarily define that. And we can kind of say, let's just define that as equal to 1, right? There's no natural number here. 0 is not a natural number. But in case we do get a 0 factorial, we'll just define that to be 1. But factorials get to be useful when you have a large chain of these consecutive decreasing values. Like what if it's 100 factorial? You're not going to go in a calculator and type 100 times 99 times 98 times 97 times 99, so on and so on and so on. Your calculator may have a built-in factorial function to help you calculate that. Okay, so with that in mind, we can use factorials to help us find the leading coefficient of a polynomial function. And that's going to bring us back to nth differences, your first and second differences. Remember those from a table of values from previous years? So we're going to find the nth differences for a polynomial of degree n, where n is a positive integer. And we're going to find that those differences are equal or constant. that indicates to you kind of what degree that is. And this the nth differences will also have the same sign as the leading coefficient. And with that in mind, you can have this little formula I'm introduced to you here, that the nth difference, like your first or second difference value, that constant value, is going to equal to the leading coefficient a of that polynomial times n factorial, again, where n is that degree. All right. Now we're going to see for ourselves in some examples how this works. So hold on to that for now. Even degree polynomials. Even degree polynomial may have from 0 to a maximum of n x-intercepts or zeros or roots. Okay. So for a fourth degree polynomial function, n is equal to 4, but that function could have 0 roots or a maximum of 4 roots. So if it had 4 roots, this is what it could look like, right? 1, 2, 3, 4, 3 turning points. Again, 3 turning points, that's a degree 4 function. It could be degree 4 with 3 turning points, but only 3 zeros, 1, 2, 3. Degree 4 with 3 turning points again, but only 2 zeros because the other turning points happen above the x-axis. Here's another one with degree 4, again 3 turning points, but only 1 zero, 1 root, 1 x-intercept. And here's one degree 4 function with no zeros at all. Everything is completely above the x-axis. Okay. So again, remind yourselves, keep making these notes. Degree, n is the degree. N is the number of zeros it could potentially have, maximum. The number of turning points is always going to be n minus 1, right? So we only have 3 turning points at most. All right. Odd degree polynomials. Odd degree polynomials have at least 1 x-intercept. It can't have 0. It has to have at least 1. Up to a maximum of n x-intercepts, where n is the degree of the function. So for a cubic polynomial, 3 is an odd number, so it's an odd degree. Right? You can have 3 zeros here, or it could have 2 zeros, or it could just have 1, but never none. All right. So remember your key features, right? If it's positive even function, starts in quadrant 2, ends in quadrant 1. It's a negative leading coefficient, it starts in quadrant 3 and ends in quadrant 4. And if it's an odd or odd function, if it's a positive leading coefficient, starts at 3, ends in 1. And if it's a negative leading coefficient for an odd function, starts at 2 and ends in 4. So you can always use the parabola and the line as like your basis for helping you remember these key features. Okay, let's look at some of the lesson examples here. For each table, determine 1, the degree of the polynomial function, the sign of the leading coefficient, and the value of the leading coefficient. And this time I'm not throwing in graphs at you. You're going to have to use a table of values. So here in this first table of values, we're going to recall, how do we do first and second differences? You have to kind of do your first difference. So let's write here first difference. And if you remember how to do the first differences, you take consecutive y values and you subtract them. So negative 12 minus negative 36, which are equal to 24. Negative 2, take away negative 12, which would be 10. And then 0, take away negative 2, which would be 2. 0, take away 0 is just 0. 4, take away 0 is just 4. 18 take away 4 is 14, and then 48 take away 18 is 30. Yeah, 30, not 20. Okay, so I hope you get the idea, right? Reminding yourselves how to calculate first differences. Then you can do second differences. This is now grade 10, right? Quadratics. So again, first differences, you check the first differences. Are they the same? No, they're all different numbers. It's not a linear function. So that's why we proceed to the second differences. So you go 10 consecutive y values again, or consecutive first differences values, as I should say. 10 minus 24, negative 14. The next pair of consecutive differences, 2 minus 10, negative 8. And then 0 minus 2, negative 2. 4 minus 0 is 4. 14 minus 4 is 10. And 30 minus 14 is 16. And again, you look at the second differences here, and they are all different values. They're not a constant value, so it's not a quadratic table. Okay, so we can keep going now. In grade 12, we can keep going to find the third differences. Okay, so third differences are just the difference between the consecutive second differences. So -8, take away -14, be wary of the double negative, we get 6. -2, take away -8, we get 6. 4, take away -2, again, a double negative, we get 6. And then 10 take away 4 is 6, and 16 take away 10 is 6. And if if you happen to get one of these numbers not 6, you just double check your work, maybe you missed a double negative or something like that. But here we see all constant 6. So this is a cubic. Third difference is constant. So it is of degree 3. Okay. So first question, degree of the polynomial. Second question, sign of the leading coefficient. The sign of the leading coefficient is going to be positive because all of these differences here are positive. 6, 6, 6, 6, and 6. Positive. So degree 3, positive leading coefficient because the third differences are also positive. Okay. And then the value of the leading coefficient, that's where the new formula comes into play, right? We said the nth differences is equal to a times n factorial. So what is the nth difference? We're talking about the third difference. The third, because it's degree 3, the third difference. That third difference has a value of 6. And that's equal to our leading coefficient a, which we don't know yet, which we're trying to solve for, times n factorial. And if it's a degree 3, we're going to say here 3 factorial. Okay. And if I rearrange this for a, I can say here a is equal to 6 divided by 3 factorial, or 6 divided by 3 times 2 times 1. 3 times 2 times 1 is just 6. So 6 divided by 6 is just 1. So a equals 1. My leading coefficient is a positive 1. So that's how we can calculate that leading coefficient. Okay, let's look at another example. Another table of values. Okay, and I'm gonna do this a little bit more briskly. So calculating the first differences, right? -8 take away -54 is 46. 0 take away -8 is 8. 6 take away 0 is 6. 22 take away 6 is 16. 36 take away 22 is 14. 12 take away 36 is -24. And -110 take away 12 is -122. So not a linear function, obviously. But let's look at the second differences. Let's see if those are constant. 8 take away 46, so we get -33. 6 take away 8 is -2. 16 take away 6 is 10. 14 take away 16 is -2. -24 take away 14 is -38. -122 take away -24 is -98. Second differences are not constant as well, so we have to keep going. Third difference is the third difference, the one that's going to give us a constant. Let's see. -2 take away -33. Oh, sorry, this is 8 take away 46 is 38. Sorry, let's fix that. Be careful. So -2 take away -38 is 36. 10 take away -2 is 12. -2 take away 10 is -12. And -38 take away -32 is 36. And this one here will be -60. Not quite yet. No, these are not constant. Well, we can keep going. Fourth difference, right? 12 take away 36, -24. -12 take away 12 is -24. Looks promising. That looks like it's -24, and this is also -24. So it looks like we've got a constant fourth difference. This is a fourth degree function, right? N is equal to 4. The constant first differences, sorry, let's talk about leading coefficient. The leading coefficient of my polynomial is going to be negative because the fourth differences are negative. All right. Fourth differences are negative 24 equal to a times 4 factorial. Solving for a, we get a equals negative 24 over 4 factorial, which is negative 24 over 4 times 3 times 2 times 1. And so a equals negative 1. 4 times 3 times 2 times 1 is just 24. 24 divided by 24 is 1. So a equals negative 1. That's our leading coefficient. All right. Look at another example. For each of the following, decide if the function is even or odd. Leading coefficient is positive or negative, and determine the least possible degree of the function corresponding to the graph. And so I'm just going to kind of review a couple of these examples we did last lesson. But remember, looking at end behavior, starting at quadrant 2, ending in quadrant 4. Crossing the x-axis here, this is going to be an odd degree function. Odd degree, should say here. Even function and odd function is still quite different. Is this an odd function? No, because even though it passes through the origin, it is not symmetrical about the origin. Is the leading coefficient positive or negative? Well, in this case, the leading coefficient is negative because it starts at positive infinity on the left and goes to negative infinity on the right. So again, recall the equation of a line, or the graph of a line, y equals negative x. That's a negative leading coefficient. It starts from quadrant 2 and goes to quadrant 4, and that's an odd degree function. So determine the least possible degree of the function. If I see 2 turning points, then 2 turns equals degree 3, least possible degree. Okay, it can't be a quadratic, it can't be a linear, right? The turning linear functions don't have turning points. The degree function could have 2 turns. Okay, and looking at B, we have end behavior both positive, 3 turning points, and the least possible degree is 4. This looks like a even degree function. Okay, so degree 4, least possible degree, could be higher than 4, but the least possible is 4. 3 turning points. End behaviors are both positive infinity, so we can say this leading coefficient is positive. Okay, positive. And is this an even, or is there any symmetry? No symmetry here. Okay. Okay, let's look at another function. Sketch the graph of a polynomial. You can do some curve sketching in this course too, perhaps. We should need to learn it anyways. So let's look at an example here. Sketch the graph of a polynomial function that satisfies each set of conditions. Degree 5, part A, degree 5, positive leading coefficient. And then 3 zeros and 4 turning points. Okay, so how can we do a question like this? Degree 5 with 4 turning points, positive leading coefficient. So think about what other odd degree functions we know. We know the basic linear function. If it has a positive leading coefficient, like y equals x. So you have to start in quadrant 3 and end in quadrant 1. Okay, so start in quadrant 3, maybe somewhere here, end quadrant 1, and somewhere there, and we have to have 3 zeros. Put in some zeros. Okay, and then we have to have 4 turning points. Let me make something like this. Doesn't matter where you put them. So we're going to cross the x-axis there. We're going to turn, cross back the x-axis, then turn again. That. And maybe before we go up again, we can turn again like that. There you go. So here I have 1, 2, 3, 4 turning points. And then 1, 2, 3 zeros. And behaviors follow a positive leading coefficient, and that's degree 5. Okay, it doesn't have to look like that precisely. Okay, it could be any combination of 3 zeros and 4 turning points. Okay, and how do you know it's a turning point? Again, these are max points, local max, local mins. All right. Degree 4, leading negative leading coefficients, 2, 0, 1 turning point. Okay, so degree 4, even degree. Think of your parabola. If it's a negative leading coefficient, negative x squared, it has to end in quadrant 3 and quadrant 4. Okay, 2 zeros, 1 turning point. So let's put 2 zeros. Okay, and with a little experience, it kind of you'll know how to really draw something that looks like this. So here's a kind of a quartic function that satisfies the condition. So it's going to have only 1 turning point up there. It tends to be a little bit more flat, but really it's not. It's still a turning point. Okay. If you ever graph something on Desmos, like y, this is probably something like y equals negative x to the power 4. Okay. You can graph that on Desmos to have a look for yourself. But the bigger the exponent, even exponent, the more flatter that turning point looks, but still a turning point. Okay, let's look at another example. Degree 3, negative leading coefficient, 1, 0, no turning points. No turning points, huh? Well, that would look something like this. So you're going to study something called an inflection point in calculus, where the graph changes its curvature. So it's not a turning point because it's not a local max or min, okay, but it is still a 0, and it's still reflective of the fact that it is a degree 3 cubic. Okay, and this would be kind of the graph of y equals negative x cubed. Okay, so no turning points means no max or min. Negative leading coefficient starts at quadrant 2 and ends in quadrant 4. All right. Question example 4. Use the degree and sign of the leading coefficient to describe the end behavior. Determine the value of the constant finite difference and state which finite differences will be constant. So number 1, part A. Y equals negative 5 times x to the power 7 minus 2x plus 1. So you want to make sure your polynomial is in order of degree, just to make sure you understand that that term is the one that kind of indicates to us a lot of the information we need. Okay, so it's a negative and of odd degree. So if it's a negative and odd degree, it starts at 2, starts at quadrant 2. And then it will end at 4. So the end behavior is as x approaches negative infinity, y tends to positive infinity. And as x approaches positive infinity, y tends to negative infinity. Okay, number 2, if the degree is 7, n equals 7, and your leading coefficient a is negative 5, then what's the finite difference? It's the 7th difference is going to equal to negative 5 times 7 factorial. Okay, and so negative 5 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, that's going to be a big number. I think it's 5,040. And when you multiply that by negative 5, you get negative 25,200. Very big finite difference. And state which finite difference will be constant. That will be the 7th difference because it's degree 7. Okay, let's look at another function, 6x minus 5x squared. So again, don't look at this. It's not right. 6x is not the leading term. It's going to be negative 5x squared. So I'll just rearrange it like that. Okay. The leading coefficient is negative 5. The degree is 2. If I look at that exponent, n equals 2. Okay. So a negative even degree function means we start at quadrant 3, starts at quadrant 3, and ends at quadrant 4. So as x goes to negative infinity, y goes to negative infinity, and as x goes to positive infinity, y goes to negative infinity. Okay. Since the degree is 2, the constant finite difference, it would be the second differences. Okay, so we're going to say here, the second difference is equal to a times n factorial. So let's put in the values right away. Negative 5 times 2 factorial. 2 times 1 is 2 times negative 5 is negative 10. So your constant second difference is going to be negative 10. So imagine doing a table of values, second differences would be negative 10. All right, let's look at another example. I think this is the last one, right? Yes, so use n behaviors, turning points and zeros to match each polynomial equation with the most likely graph below. Explain, state the number of x-intercepts, the number of maximum and minimum points, the number of local maximum and local minimum points. How are the features related to the degree of the function? Okay, so what kind of approach would you take? Well, you can look at the function first and try to match it with a particular graph. Okay, so if I look at the first one, 2x cubed minus 4x squared plus x plus 1, I have positive leading coefficient with an odd degree term there. So it's an odd degree function. So it's going to start at quadrant 3 and end at quadrant 1, right? So again, if you have a hard time visualizing it, just, hey, imagine the line starts at quadrant 3, ends at quadrant 1. Okay, is there a graph that starts in quadrant 3 and ends at quadrant 1? Looks like number 3. Boom, done. We've got it. Okay, that matches that one. Part B, g of x equals negative 4x squared plus 10x squared plus 5x minus 4. Even degree function, negative leading coefficient. So it's going to start at quadrant 3 and ends at quadrant 4. Is there one that does that? Yeah. 1. Okay, want to verify? 3 turning points. 1, 2, 3. So that means the number of degrees, the least degree is 4. So that works. Okay. H, part C. So that's going to be, this is a graph number 1. Okay. So we eliminated those two. So let's say h of x, negative 2x power 5 plus 5x cubed minus x. Negative 2 leading coefficient, odd degree. Looks like we're going to end, if it's going to start at quadrant 2 and end at quadrant 4, it's going to be this one right here. Every term is an odd degree term. So that's point symmetry about the origin, which we do see here. So that will match that graph. And then P of x, well, just by a process of elimination, that will be 2. But if you just want to verify, hey, you know, it's odd degree, sorry, even degree function, and behaviors are going to be in the same direction, positive leading coefficient, so y values are going to be positive infinity. Okay, great. And we have that going for it. And that's it. All right, so there it is. That's how we can answer that kind of a question. Some more homework problems to look at from the textbook. And again, these are just say the minimum, try and do more questions for more practice, especially if I say 1 A, B, C, D, E. Okay, if I say 3 A, B, D, F, maybe try C and E as well. Okay, if you have time. But at the bare minimum, try these questions here and come to class with questions. That's the end of this video. See you in the next one.